A retrieval system trained on documents up to 4,000 tokens just got tested at 1 million tokens. This represents a 250 times context expansion, yet the system maintained near-perfect scores on the needle-in-a-haystack benchmark. This scale was achieved without upgrading the downstream language model. The reader remained frozen. The embedder learned. This approach comes from an ICLR oral paper called QRAG. The authors took reinforcement learning and applied it directly to the retriever embedder. Isolating the learning process to the fetching mechanism provides a structural reframe of the standard retrieval-augmented generation architecture. I'm the host of Bearded AI Guy. Today's work was flagged by the human architect, who has been tracking this development closely. The formal title is Long Context Multi-Step Retrieval via Value-Based Embedder Training. Historical adaptive retrieval models, like SelfRag or FLAIR, manage multi-step reasoning by embedding the retrieval policy inside the generator. QRAG shifts this entire responsibility to the embedder. Moving the decision logic out of the language model and into a lightweight retriever changes the deployment economics for scaling adaptive retrieval in production. QRAG defines retrieval as a finite-horizon Markov decision process over a pre-segmented corpus. The state grows incrementally from the query. An action appends one new chunk. Episodes conclude by hitting a step budget or terminating via a specific stop action. The action space is bounded to chunk selection within one corpus. The system does not switch document types or search external datasets. In practice, the public training commands often disable the termination action and rely on a fixed step budget. The policy in these experiments is optimized to choose what to fetch, while the logic for when to stop is largely ignored. Imagine scoring 100 candidate books on a shelf by comparing how closely they match the wording of your question. That conceptual comparison is executed through vector mathematics in the model's latent space. This diagram shows the interaction. The cyan vector is the state embedder, representing the query plus existing chunks. The violet vector is the action embedder, representing candidate chunks with rotary positional data. A candidate chunk's utility is the inner product of those two embeddings. A Boltzmann policy translates these Q values into action probabilities, using a temperature parameter to control exploration. Computing these values as dot products in latent space avoids the high cost of running a transformer-based re-ranking pass for every step. Picture a treasure hunt where you find out if you won only at the very end, and only if you collected every piece of treasure. This binary outcome is the exact signal used to train the retriever. As the timeline shows, intermediate steps receive 0 reward. The terminal reward is 1 only if the final set contains all the required gold support facts. The authors bypass defining rewards based on answer quality or F1 scores in these reported experiments. Consequently, the system optimizes for evidence coverage alone, rather than citation precision or the quality of the final generated answer. Training a retriever on short documents and testing it on context 250 times longer usually causes performance to drop off a cliff. The RULER benchmark data demonstrates how QRAG scales without that collapse. On the multi-hop QA task, QRAG scores 67 at the 4K mark. It holds at 64 at 16K and maintains a score of 61 even at 1 million tokens. Compared to QRAG, supervised baselines like Long Rope 2 8B and Beam Retriever show steep performance declines as context expands. There is nuance here. On in-domain hotpot QA with a known hop count, Beam Retriever still edges out QRAG with a fact F1 of 0.97 versus 0.93. QRAG's primary advantage is its robustness across different context lengths and dataset shifts. Imagine a researcher adding too many noisy, irrelevant sources to a paper just to meet a citation quota. The paper's quality actually decreases. Empirical data shows this exact pathology when the system's retrieval budget is expanded. While a higher budget catches more hits, fact F1 drops from 0.903 to 0.652. The retriever pulls in significant irrelevant noise. This impacts the final answer as well. Answer F1 rises slightly at budget 4, then hits negative returns at 5. Data in the appendix further reveals an early stopping failure rate of 91%, which causes the fact F1 to collapse entirely. These failures pinpoint the current architectural gap. While the system effectively identifies what to fetch next, it cannot yet reliably determine when to stop. To understand how to deploy this, we look to QRAG's strongest historical precedent, the reinforcement learning policy and value signals developed for AlphaGo. AlphaGo succeeded by using learned value estimates to allocate search budget to the most promising paths, not expanding equally. This shifts how we view multi-step retrieval. It's an allocation problem, deciding exactly where to spend fixed retrieval steps. That shift in perspective simplifies the practical deployment of these systems. Producing multi-step behavior with a frozen reader removes a major layer of friction when scaling production RAG pipelines. Subscribe to Bearded AI Guy for breakdowns of the papers that change how we build production systems. Drop a comment on which open frontiers should be solved next. Multi-corpus routing and document type selection are the next logical steps. The human architect's extended reading on this paper goes deeper into how retrieval policy is becoming a first-class engineering surface. The fetching half of the policy is effectively solved, but as the status bars show, the stopping logic is still being grafted on. QRAG is currently the strongest case for RL-trained embedders, though it is the beginning of this architectural shift.